Hi everyone, today we're going to build a green screen remover. Basically, how to remove a green screen from a video using WebGPU. We'll explore how shaders work in WebGPU and see what kinds of things we can build with them. Right now, I'm just experimenting with what's possible. Personally, I'd love to eventually build a full online video editor, but that'll take some time. Since that project would be too big for one video, today we'll focus only on manipulating videos with WebGPU. The idea came to me when I was thinking about how video editors remove green screens. I thought, why not try to build a simple version myself? Of course, if you don't want to dive into WebGPU, you could also use other libraries like pixie.js. I'll probably make another video about that later. For now, I'll share the code for this project. You'll find the GitHub link in the description. You can copy it and try it yourself. Don't worry. The HTML and CSS are pretty simple. Here's how the project is structured. Main.ts adds event listeners and starts the project. Green_screen.ts contains the green screen class that handles the effect. Before we jump into the class, let's look at the shader code because that's where the real magic happens. The class itself is pretty straightforward. The only tricky part is figuring out how to download the processed video after removing the green screen. Right now, that's still a work in progress, but the effect itself works nicely. Alright, let's look at the vertex shader first. This code is simple. We're just creating a square with 6 vertex points. This square is where the video frame will be drawn. Since it's a square by default, we pass a scale value to make it a rectangle that fits the video properly. Let's take an example. Imagine we have a square with points from -1 to 1 in both x and y. If we want to turn it into a rectangle, we multiply the x and y values by a scale factor. If scale.x does not equal scale.y, the square stretches into a rectangle. Increasing scale x stretches it horizontally, increasing scale y stretches it vertically. Multiplying both by values less than 1 shrinks it, while values greater than 1 make it larger. In the green screen class, we calculate the scale based on the video's aspect ratio, then multiply it by 0.5 so it fits nicely inside the canvas. Now, let's see what's happening next. We create an out variable and set its position and UV coordinates. The UV coordinate system is different from clip space, so we need to convert it. Clip space goes from -1 to 1, but UV coordinates go from 0 to 1. For the x position, we add 1 to convert -1 to 1 to 0 to 2, then multiply by 0.5 to get 0.1. For the y position, we do the same but flip it \1 minus y, otherwise the video would appear upside down. This ensures the video frames map correctly onto the rectangle while keeping the correct aspect ratio. Now let's move on to the fragment shader, the most important part. This is where the actual green screen removal happens. We check each pixel of the video and decide whether to keep it or make it transparent. At the top, you'll see we have sump and text. Text is our texture. Basically, the current video frame uploaded to the GPU. You can think of it as an image where each pixel has a color. Sump is the sampler. Its job is to tell the GPU how to read pixels from the texture. Imagine you're asking, "Hey GPU, give me the color at this UV coordinate." But what if that UV coordinate doesn't map perfectly to the center of a pixel? The sampler decides whether to grab the nearest pixel or blend between nearby pixels for a smoother look. So the sampler defines the rules for reading pixel colors from the texture. Now let's connect this to the sampler we created in our class. In our code, we have something like this. This is the JavaScript and TypeScript side, the part where we tell WebGPU how to handle textures. MinFilter controls what happens when the texture is displayed smaller than its original size. MagFilter controls what happens when the texture is enlarged or stretched. We set both to linear, which means blend smoothly between pixels, instead of picking the nearest one. That avoids blocky edges and makes the video look soft and smooth. Here's what's actually happening. First, text is our video frame. Second, sump applies the sampling rules, in this case, linear filtering. Third, UV is the coordinate where we want the pixel color. Fourth, texture sample combines everything and gives us the RGBA pixel color. You can think of it like this. Texture sample takes the video frame, applies the rules we defined in create sampler, and then returns the pixel color at the given UV coordinate. After that, the rest of the shader handles the actual green screen effect. We define our key color, pure green Then we calculate the difference between the current pixel and that green color. We use a threshold, how green it needs to be before we remove it, and a softness value for smoother blending. Smooth step helps make the transparency fade naturally instead of cutting harshly. Finally, we return the pixel's RGB values plus the new alpha. And that's it. The fragment shader goes through every pixel of the video, checks if it's green, and if it is, makes it transparent so the background shows through. Okay, now let's move on to the class. And it's actually pretty simple. We have a constructor where we take in a canvas, then in the init function, we kick off the whole effect. Here's what happens step by step. First, we take the video file and create a hidden video element. Second, we attach event listeners to know when the video is ready or if something goes wrong. Third, we autoplay the video. Otherwise, we'd only see a still frame instead of the video playing. Then once the video is ready, we grab its width and height to know the actual dimensions. Then we set up the WebGPU device and pipeline. Both are pretty easy to follow. We create the sampler so we can properly read pixel data from the video. We create a texture that matches the video size. Finally, we start the render loop using apply effect. So the init function basically does all the setup. It loads the video, plays it, prepares WebGPU, and then starts the green screen effect. We've already looked at the create sampler function, so now let's jump into the create or replace video texture function. This one's also easy to understand. First, we calculate the aspect ratio using getAspectRatio. That function simply figures out how much we need to scale our square, so the video fits nicely inside the canvas. If the video is wider than the canvas, we scale down the width using video aspect divided by canvas aspect. If the video is taller, we scale down the height using canvas aspect divided by video aspect. So basically, if the video is wide, shrink the width. If the video is tall, shrink the height. After that, we take the scale values, put them into a buffer, and send that buffer to the GPU. This buffer is passed as a uniform to the vertex shader, so the shader knows how to stretch or shrink the quad, the rectangle we're drawing the video on. Then comes the texture part. If we already had a texture before we destroy it, it's just good practice so we don't leak memory. Then we create a new 2D texture that matches the video's width and height. Important point to notice is that video texture is where each video frame gets uploaded to the GPU. You can think of it as a GPU side copy of the current video frame. Every time the video updates, we copy the new pixels into this texture. And since the fragment shader samples from this texture, that's how we actually see the moving video.
Finally, we create a new bind group. This is how we connect all GPU resources like sampler, texture, and scale buffer to the shader. Here's the mapping, binding, 0 is the sampler, and this tells the GPU how to read pixels. Binding, 1 is the texture, and this is the actual video frame on the GPU. And lastly, binding, 2 is the scale buffer, which is the aspect ratio values for the vertex shader. So that part's done. Now let's look at the apply effect function. This one's also pretty simple, even though it looks a bit long. What's happening here is we're starting a render loop that updates every frame of the video. Let's break it down. First, inside the frame function, the first thing we do is check. This just makes sure the video actually has data ready, so we don't copy empty frames. Then we copy the current video frame into our GPU texture. Here, the source is the HTML video element and the destination is our video texture on the GPU. So basically, every frame of the video is uploaded to the GPU so that the shader can use it. After that, we create a command encoder and start a render pass. This is where we tell WebGPU, hey, clear the canvas first. That's what the clear value does. Now draw using my pipeline and bind group. Then comes the draw call. Here 6 means we're drawing 6 vertices which form 2 triangles, and together those triangles make a rectangle, the quad where the video is displayed. Once the draw pass is done, we finish and submit it to the GPU queue. Finally, at the end, we call request animation frame function. This tells the browser run this function again on the next frame. So this creates an infinite loop, and on every frame it copies the latest video frame to the GPU texture, runs the shader pipeline and draws it back onto the canvas, and that's it now video plays smoothly with the green screen effects applied in real time. Now let's look at the last function, downloading the video. This function is called start recording, and the idea is simple. We record whatever is being drawn on our canvas and then save it as a video file. Let's go step by step. First, capture the canvas as a media stream. This line turns our canvas into a video stream. So everything that's being drawn on the canvas, like our video with the green screen, removed it now, acts like a live video feed. Second, create a media recorder. Here we create a media recorder object that takes our canvas stream and records it. We're using the WebM format, which works well across browsers. Third, store the chunks. The recorder doesn't give us the whole video at once. Instead, it sends it in chunks over time. We just collect those chunks into an array. And lastly, when recording stops, make a video file. Once recording stops, we combine all the chunks into a single blob, basically a video file in memory, and create a temporary URL that points to it and trigger the download. We create a hidden tag, link it to our video file, set a file name, and automatically click it. That triggers the download. Now for cleanup, we release the memory used by the temporary file URL and start recording, and when time's up, stop recording. We start recording right away and automatically stop after the given time. Default is 5 seconds. You can pass a custom duration milliseconds if you want it longer or shorter. So to summarize, this function records the canvas output in real time, collects the data into chunks, lets you download the final video as a .webm file. That means your green screen effect doesn't just stay on the canvas. You can export it and actually share the processed video. And that's it. We've successfully built a simple WebGPU project that removes the green background and even lets us adjust the threshold and softness in real time. This gives you a solid foundation, and from here you can start adding your own effects or even chain multiple shaders together. The full code is on GitHub, the link's in the description. In future videos, we'll keep improving this. For now, this was just a small project I wanted to share with all of you. Also, as you probably noticed, that the video recording / export feature isn't perfect yet. I'm still exploring ways to export with better codecs like H.265 or something similar. So if you have any suggestions on that, please drop them in the comments below. I hope you liked this video. Please don't forget to like, share, and subscribe for more. Thanks for watching, and I'll see you in the next one.